is going to be and to continue about the geometric.
Okay. Can everyone see this and read it? Okay. It's all right? Fine. So this is about geometry of gradient flows, or gradient flows of geometric objects. And we've been looking at equations for aggregation of particles in which there's a competition of length scales. This is a rather old problem, goes back into the 1920s. And we're going to use now a variational method that's based on Felix Otto's analysis of the Darcy law for the porous medium equations. And we're interested in the formation and interaction of singular solutions. So we showed before, something's missing. Okay, never mind. So these are collaborators. What we showed before is that there were two main ideas of this in this talk, that non-local mobility, so that say you have a mobility that depends on the density, but in fact it's a smooth version of the density. It leads to singular solutions. And we used the Keller-Siegel model as an example of how this works out, because Keller-Siegel comes with a non-local mobility. Okay, and so that's idea number one, which we talked about in the first two lectures. And idea number two is that variations of geometric objects such as tensors, vector fields, etc., depend on how they transform. How they transform under smooth maps. So, in particular, delta rho depends on what rho is. Okay? Whether rho is a vector field, a density, a scalar, a tensor. By their transformations shall you know them. Okay, you ask what it is, but it's transformation. Okay, so its transformation, its variation is d by ds at s equals 0 of rho depending on s. Okay, but since it's a vector field, I'm sorry, it's defined on, this rho is defined on some space. So we give it coordinates x, and so we want to know is how does rho vary when we vary x. That's what we mean by the transformation property of an object. Function, density, vector field, tensor. They all transform differently. And in fact, tensors, vectors, everything, the geometric objects that can be acted on like this are defined by how they transform. That's what you mean when you say something is a vector. It's how you transform it under some flow. Okay, and so, and this guy here, this is the variation. So we're talking about, oh, Robert, I need this raised. We're talking about, stop, okay. We're talking about variational principles. And so we have to know what we mean by taking variations. And taking variations of one type of object will give us a different result than taking variations of another kind of object. That's what we're paying attention to. That's the key idea. Okay, so in the first lecture we talked about Cahn-Hilliard equations in 1D, 2D, 3D. We talked about what happens when you stir the Cahn-Hilliard and dynamics so that one part of it is trying to demix, but when you turn on the stirring, it tries to mix, and there's a competition between them. We talked about chemotaxis and how sometimes the results of an equation like the Keller-Siegel equation look sort of like Cahn-Hilliard, but other times they blow up. So we talked about blow up. Okay. We talked also about how the behavior of the solution depends on the mobility, and that the blow up occurs when the mobility is a non-local, so smooth function of the thing which is evolving, the object that's evolving. Okay, we said a little bit about magnetic particles and how they aggregate or clump. So these are like, act like particles and they clump, so they're called clump-ons, right? Like Klingons, but clump-ons. Okay, and so this is the equation for the density, the magnetization density. And these are particles. They act like particles because they are being carried along and transported by the same velocity, v. Okay, so that's where we stopped. And I'll come back to this one later. Okay, this is where we, so I guess I'm done with this for a while. Okay, so here's the start. Could you not hear me before? Here's the start. I'm going to talk about geometry of gradient flows. Okay. So we write them in what's called their weak form, and we use thermodynamics to help with the definition. Okay, so here they go. d by dt of a quantity rho, when rho is a density, in this case, is paired with some smooth function phi, and this will be L2 pairing, multiply, integrate. is equal to the divergence of rho times some velocity, depending on phi, paired with dE d rho. So this part is going to give us the gradient flow for a density that we know. And here's the key idea. Okay, this guy is the pairing of delta rho with dE d rho. It's going to be this delta rho. It's going to be a delta rho which is defined by how it transforms infinitesimally. Okay, and so this is going to go to a critical point of the energy, right? d by dt of rho will stop when dE d rho is 0. And this is the whole idea. This is how we get geometry into this problem. So from here to here, rho can be anything as long as we say delta rho is this quantity. Okay, so to work it out a little bit, you're pairing with phi. The function is phi in here, so we can write this as d by dt rho phi. So what do? We have L2 pairing. So we bring the gradient over, we bring the rho over, and we write v, that's Darcy's law, of mu of rho times the gradient of phi. This then becomes, I'll do it in 2 steps. So minus v of phi paired with rho grad dE d rho. And that's this guy. Bring the mu over, take the grad over, and change the sign again. We have phi paired with, let's see, what are we doing? We're taking the mu over and the grad over. The grad gives us, when we take it over, it gives us a divergence. Rho, mu of rho, grad, dE d rho. And this is the gradient flow of a density that we know. Okay, just checking. The key idea here at this stage is we put in Darcy's law for the velocity that goes here. Okay, the next key idea is going to be this delta rho is written this way. Why is that? Okay, anybody know why that is? Okay, I'll tell you. Let's see. Lee derivative with respect to v of phi acting on rho times d3x, because it's a density, like every tensor, you have to put its basis in. Rho times d3x, not just rho of x, it's a density, so you have to keep track of it. Now, I was talking with Uwe about that, and he said, aha, so this is the difference between an extensive variable and an intensive variable. Temperature, is that what it is? Extensive and intensive? No. Well, this one here is extensive, and just a function would be intensive. And this Lie derivative is the divergence of rho v phi times d3x. Okay, this is this guy here, and we're keeping track of this d3x. We need to keep track of it for L2 pairing because this guy here is the integral of phi times the divergence of rho mu of rho grad dE d rho. And there's one more thing we need in order to make this pairing stick. Okay? We need d3x. Right? So you have to pair in the L2 pairing things which are dual to each other. This guy's a density, this guy's a function. Then you can pair it. Okay. So let's talk about Lie derivatives. Okay, so let's write it in a general form. Okay, so we have a Lie derivative has a definition. So they arise from tangents to flows on manifolds. So here's an example of a flow in a manifold. So let G sub t take the manifold M into itself. Okay, and let G sub t compose with G sub s. Here's the definition of a flow. Equal G sub t plus s and G at 0 is the identity. This makes for a very nice flow because it's associative, right? If you now hit it with another one, it's associative. It has an inverse when s is equal to -1, right? It's a bilinear operation. So actually, this is the definition of a group. It's a flow that has these properties. Okay, then the Lie derivative of some form alpha with respect to a vector field V defined on M, alpha and V on M. Right, so it's a Lie derivative of this form. Respect to also means along. Right, so we have this flow. It has a tangent. Its tangent vector at some place in the manifold X is a vector field. It's a different quantity at each point. Okay, so the Lie derivative with respect to V of X, first of all, is d by ds at s equals 0 of x of s, which is v of x. Okay, so v is a tangent vector along the flow on the manifold. So for alpha, so let's just write what it is down for alpha. Lie derivative with respect to v for some form alpha is d by ds at s equals 0 of gs star alpha. This is what Randy in his first lecture called pullback. but it just means this. d by dt at s equals 0 of alpha of x of s. Right? So we write x of s is gs acting on x at 0. So what's this object? Right. It's the variation. Right. You tell me, give me any form, any tensor, anything you like, and this guy here will be the variation of it along some flow. We're going to use this to derive the properties of gradient flows of anything. Okay, some examples. So the variation of a function, f, on the manifold. Well, actually, let's just do this on some, just think about it as on space taking us into real numbers. But it could be any number of dimensions. But just take one-dimensional guy on this side. Delta f is the lead derivative with respect to v of f, which is d by ds at s equals 0 of f of x and s, which is equal in turn to grad f of x, now when s equals 0, dot what? Dot dx ds. Right? But that, evaluated at s equals 0, but that's equal to grad f dot v. Right, this is the variation of a function in this direction v, and it's also the definition of the gradient. Okay, functions. Let's do densities. Densities are one of our favorite things. So I'll do a density rho, which takes R3 into densities on R3. Okay, so delta rho is the lead derivative with respect to v of rho times d3x, which is d by dt, d by ds at s equals 0 of rho of x of s d3x of s. This is the point I want to make, that when you're dealing with a tensor or density or anything like that, that's not just a function, it has a basis. Okay, in order to make it into a geometrical object, you have to say how it transforms. Okay, so this guy then is like the function. It's grad rho dot v times d3x plus rho. So this is derivative. It has a, we can use the chain rule. Rho times d by ds at s equals 0 of d3x of s. This guy is grad rho dot v, and this is with, right, keep this in mind, the v is dx ds at the identity s equals 0 plus rho times this quantity. Okay, this quantity is also the lead derivative with respect to v of the volume element x. And that this quantity here is the divergence of v times d3x. If you just substitute into d3x that dx1 of s, dx2 of x, dx3 of x, and you act on it with this derivative, keeping in substitute dx ds for v, you'll get the divergence. And when you evaluate it, s equals 0 times the original volume form. And this is the definition of the divergence. Okay, so let's finish it. This guy's div v times d3x, which is equal to the divergence of rho times v times d3x. Delta rho is that divergence. That's the thing that gives us the gradient flow that we're familiar with. Okay. Some more about this key idea. Okay. So, key idea. Use lead derivative with respect to v, depending on your pairing function phi, acting on whatever you have, some symmetric object, in your variation. And compute. So, when you compute this, you'll have d by dt of kappa paired with phi. So phi has to be in a dual space of kappa. For every tensor, there's a dual tensor that when you contract over the indices, you get a real number. That's a pairing. And in our case, we're also integrating over it. Okay, so phi is in a dual space to kappa, and we write this as delta kappa paired with the d kappa. Okay, kappa is in one space. The d kappa downstairs is in a dual space. Okay, so let's write that. Oh, this is a symmetric pairing. So we can write this as the d kappa paired with delta kappa also. Right? Because the L2 pairing is symmetric. It doesn't matter what order we write. So let's write this one as the rho, kappa, the kappa paired with minus the lead derivative with respect to u of phi, some velocity, times, I'm going to put here the mobility, which could be non-local. Okay, and now we have to stop because we haven't defined what the thing corresponding to gradient or divergence is for any tensor. For any tensor, that thing is actually called diamond. And so let me talk about the diamond. The definition of diamond. Any questions at this stage? Who never heard of Lie derivative before? Ah, okay. Most people did. It's a directional derivative of some kind of tensor. Oh, okay. So we talked about gradient. Well, we talked about divergence. We talked about Lie derivative. And now we're going to talk about diamond. It's some kind of operation. Okay, so consider a pairing of the quantity A with minus the Lie derivative with respect to a vector field eta acting on B, where A and B are dual to each other in the sense of, for example, that's a contravariant vector, that's a covariant vector. And the duality is a dot product and then integrate. So we start with this guy. We define diamond this way. A diamond B paired with eta. Okay, so this thing is defined in some vector space crossed into its dual. This thing is the element, it's a vector field, so it's an element of a Lie algebra. And this thing here is dual to it. So, so what's a dual to a vector field? Right, okay, I'm only going to say this because we really need it for explaining the general position here for tensors. Vector fields insert into forms. Things which are dual to vector fields are densities. Okay, sorry, are one forms. Okay, and more than that, they have to carry that d3x around with them, and it's called a one-form density. When you insert the vector field into it, you get a dot product, and then you can integrate it because you have left over the d3x. And so this guy I'm going to write as V star. But the great thing is, both of these are L2 pairings. So we can just erase where things live, because both of them are evaluated in the same space. Okay, so this is diamond. So here's Darcy's law. For densities, you say that u of phi is minus mu of rho grad phi. So now we do Darcy's law for geometric objects. So this will be u. Oh, actually, I have to say one more thing. So u is a vector field, so it's a contravariant vector. Grad is actually, it's a one form, and it's a covariant vector. So to raise the index from lower to upper, so it matches the index on both sides, you introduce this little operation called sharp, which raises indices. It's not a Riemannian metric. It just raises indices takes you to the dual space. So you can write u of phi is minus mu of kappa diamond phi. And now for each object, you write as a Lie derivative, and put it in here. Okay, integrate by parts to get it into this form, to take it, get eta on one side. That's the diamond operation between A and B. For densities, it's a gradient. For it's a gradient of what? For densities, it's a gradient of a function times the density. Sharp. For functions, it's the variational derivative. Well, it's for functions, this guy's going to be on the other side. It's going to be phi grad mu. And you'll see in a moment that it makes all the difference in the simulations. Okay, so this is the new Darcy's law. You give me a tensor, you give me anything. Tell me how it transforms. Okay, transforms by Lie derivative. Okay, I will compute diamond, and then I'll use that to create my gradient flow for such an object. So this guy is d80 kappa diamond phi paired with d80 kappa diamond mu of kappa paired with u of phi. Okay, so it looks the same. We replace. It looks the same as for functions. And let me mention some of the properties of diamond, so we can compute with it. Properties of the diamond operation. It's much like you compute them by integrating by parts. Okay, so one, diamond is antisymmetric for L2 pairing. Just like when you integrate by parts, you change the signs. It's antisymmetric, and that means that B diamond A plus A diamond B paired with some vector field is 0. So we can replace B diamond A with minus A diamond B. Okay, 2, diamond satisfies chain rule. For Lie derivatives. Remember, our variations are going to be Lie derivatives, and we're going to have products like B diamond A and A diamond B. We need to be able to take the variations of them and regroup them, and we can do that because Lie derivative with respect to C of B diamond A paired with eta is the Lie derivative with respect to C on B paired with A plus B diamond Lie derivative with respect to C on A paired with theta. So it satisfies the chain rule. And those are the things we need to finish this calculation. So this is, first we use antisymmetry. So this is mu of kappa diamond d kappa with the minus sign paired with u of phi. And that's equal to this guy. So here's where we insert Darcy's law, d kappa, minus mu of kappa diamond d kappa is paired with u of phi, which is which way does it go? Okay. Phi, okay, it's kappa diamond phi sharp. Okay, so diamond takes you into the space which is dual to Lie algebra. Sharp takes you back to the Lie algebra, and then you compare it with L2. So here's where we put in Darcy's law. This is Darcy's law for a general object. This is d kappa d phi. When the dust clears now, we're going to shift back and forth and put in some Lie derivatives. And we'll have minus Lie derivative with respect to mu of kappa diamond d kappa sharp to make it into a vector field acting on kappa paired with phi. So this is this geometric. So this applies to order parameters. Order parameters always transform in some kind of tensor. Okay, so I'm going to call this thing geometric order parameter equation, which we'll abbreviate as GOP. Okay, and it is d by dt of kappa. Now we say all the phi's are arbitrary, is minus Lie derivative with respect to mu of kappa diamond d kappa. This is the vector field. So this is we've created a vector this way, and it acts on kappa. Now you tell me, I'm done. Now you tell me what kappa was. So when you say variation of kappa, you have to say, how does it transform? The answer is it transforms by Lie derivative. We put in the Lie derivative into the delta rho, or delta kappa, paired with d kappa, so we go to a critical point. But delta rho has to be something. Put in the Lie derivative, but you have to get the Lie derivative off in order to write it in this form. So you need diamond. Okay, so these are the things we need to write a gradient flow. We need gradients for functions. We need divergences for densities. We need Lie derivative for variations. And we need diamond for integrations by parts with Lie derivatives. Okay. So then after lunch, I'll talk about some examples, okay, which again gets us back. We'll do the magnetic example like that one also. Any questions? Is that too much?
After lunch, the questions.
After lunch, yeah. Talk amongst yourselves. You know.
Okay. Let us thank you.